So what we've got, we're looking at a reaction diagram here, and reaction diagram is basically just a graph, really, but it's more like a sort of diagram of a graph. We don't actually plot this graph at all at any point, but it's something against something, and often that those somethings aren't really explained. But essentially, what it is the energy within the system, and the system is essentially whatever we happen to be studying at the time. So when I say system at this point, I mean the energy held within these particles here. So these particles are just kind of like a model to describe a reaction of some kind. In this reaction, we have two atoms bonded together, reacting with this red particle or red atom, and then they eventually become like this. But the in-between stage is when they're all separated from each other. So the energy of the system would be the energy held in these, or these, or these. That's the system. And the system changes over time, as you can see. Or during the reaction, the system changes. So the energy within the system is the thing that we're changing. And so this means that if we gave it some energy, then you can see obviously the energy would go up. And then what would happen? Apparently the energy would just drop. So what it's saying is that when I give it some energy, well, first of all the diagram is really saying is that if I gave it some energy, it would go up and then it would drop off again, and then just settle down at that new energy state. But these little bits I've added onto the diagram as an explanation. So what it's saying here is that first of all, when I give it some energy, I'm going to cause it to separate into these separate atoms, and then what happens then is the new bonds are being made to lead it to these products. Now, so what this diagram is showing us then is that I had to give it energy to break this bond. So energy is required to break bonds, but when a new bond is being made, that releases energy. So let's get that down as in our notes. So, so that's why energy had to be added to the system to break these bonds to get it into this state. But then when it went into the products, energy was released. And so that means the energy within the system dropped. So this reaction on the left is going to be absorbing quite a lot of energy to get to that point and then releasing some energy. But overall, it's going to release less than it absorbed. It's going to release, I had to give it a lot of energy, and then it gave out not as much energy as I had to give it, which meant that if there was lots of these, and of course there would be lots of these, I would have to keep giving it more energy because it's using up the energy in order to complete the reaction. So we can label this parts of this diagram. We can say that amount of energy there, that energy is the energy that I had to give it, and that's got a name. That is called the activation energy. The energy to cause the reaction to happen is called the activation energy. Now the reaction on the left looks like it's got a large activation energy. The reaction on the right, not so much. I just need to get it to that point where it gets to a hump and then it drops off again. So this one has got quite a small reaction. Well, maybe it's basically that there. That's the amount of activation energy there. Okay. And then we have a certain amount of energy released. So in this case, we're releasing that much energy. Once it's got to the point where it's about to react, it's going to release that much energy there, from there to there. Whereas the one up here, it's releasing from there to there. Okay. So that's the amount of energy released in that one. Okay, so you can see on the left, I'm giving it a lot more than the one on the right, and on the right, yes, I'm actually going to give it a little bit, but it's going to release a lot. So same sort of thing. It's basically why do we have these kind of different reactions? Well, basically because on the left I had to break these bonds, and on the right some bonds were being made, but it might be that it doesn't take much energy to make it takes a lot of energy to break this bond here, but it doesn't give out much energy when these bonds are being made. Okay, so maybe this one on the right might be the one on the left in reverse. So maybe the one on the right might be something like this. It starts off with that, then we're going to break. Whoops, we're going to break that bond to make it appear like that, and then we're going to get it to eventually go like that. Clearly, it's not quite to scale, but yeah, you can see. So we're starting off with that. We're going to break it all. Then we're going to release. It's going to release a ton of energy. So how might we experience this if this is these reactions were in beakers and we were and maybe we put a thermometer in the beakers? How might one be different to the other? So, well, the first thing to take into account is that when you're actually doing the reaction, you won't really see sort of like the up and down bit. For one thing, it's all that's happening very, very quickly, and it's happening millions of times. And one reaction, one particle or one molecule or whatever might be in a different stage of the reaction to another one. So we're just going to see the overall effect, which is essentially going to be this change in temperature from the start to the end, and from the start to the end here. So use those bits in this, and at that point we kind of, as far as experiencing the thermometer change, the activation energy doesn't really come into it. So have a think about which one would essentially get colder and which one would get warmer. So it is actually exactly the opposite way around, and a lot of people get it that way around originally because they think, well, it goes from low to high. But this is not the energy that we're getting. This is the energy in the system. So what we're detecting with our thermometer is the energy coming out of the system. Because if it's getting warm, then it means that if the thermometer is getting warm, then the system is emitting heat. It's losing energy, right? So that means that this one would be getting colder and this one would be getting hotter. Okay, so what is the name of a reaction that takes in heat, or in other words, gets colder? Or the reaction doesn't get colder. The beaker or whatever would get colder, and so the one on the left is something called one type of reaction. The one on the right is called another type of reaction. Correct. Good. So the one on the right, because it's releasing energy, it's giving out energy, then we would call that exothermic. So let's just label that. And the one on the left, let's give it a nice sort of red color with white writing. Oh, because it will feel warm. Whereas this one is taking energy in, so we'll give that a nice blue color. And this is endothermic. It's taking heat in. It needs to take heat in because making these new products needs more energy. So, breaking this old bond needs more energy than the energy released by making the new substances and the products. Whereas this is exactly the other way around. So that's endothermic. This is exothermic.